Hello guys, welcome to today's class. Today we're going to be talking about algorithmic thinking. This topic is more about logically thinking about in algorithmic way than coding. What is algorithmic thinking? If we first want to start, algorithmic thinking is a way of thinking how we can get the best output, how we can have the best solution for a problem. Suppose when we were in data structure course, we talked about finding solutions, but we never talked about finding the best solution. In data structure, our main target was getting the question and just finding the answer, no matter how we found the answer, right? But in algorithm course, it is mandatory that we start about thinking which is the optimal solution for our problem. Let's say when we want to go from point A to point B, suppose we are told to go from point A to point B. In data structure course, we are basically tasked with going from point to A to point B. Nobody cared how we went there, nobody cared how long it took. But in the algorithm course, we are required to think which is the fastest route to go from A to B. You guys get it? In today's lecture, we're going to be seeing three ways how we can solve a problem, and it will show us why finding the best solution matters. Let's say we talk about finding to checking if a number is prime or not. We all know how to find the prime or not. We have done it in our data structure class. It's a very simple solution. Uh, what we know of is a prime number. Is a number which can only be divided by one and itself. So, in our data structure classes, we basically found a solution where we talked about how to find the solution, keeping in mind that we know a prime number is a number which can only be divided by one and itself. So, knowing this, we basically came up with a solution that if we check if a number is being divided by 2 up to n minus 1 of that number, if it gets divided, then it is not a prime. If it doesn't get divided, then it's a prime. So it can be categorized as a slow solution. Let us see that solution. We can talk more about the other solutions later. So let's do uh, let's write a function which will find if a number is prime or not. Um, prime number, prime number checker, prime number checker. The parameter for this is there will be only one parameter, the number itself. In this, as far as we know, the solution we know of from our data structure classes is first we check if the number is less than or equal to 1. If num less than equal to 1, we return false, that it cannot be a prime number. Else, what we can do is uh, we can check for I in range. The range will start from 2 and up to n. We will put here num because we want to go one step before the numbers. Suppose the number is 5, number is 7, we will go till 6. And inside here, okay, I'm sorry, inside here, what we'll do, we'll check if num mod I equals to 0. That is, if any number can divide if any value of I can divide our number, we can easily say that it is not a prime number. So we can return false. Yeah. So if in the for loop, if any of the values of I can divide the num, we will return false. If this is not the case, that we go through the whole loop and there is no return, and we don't return from the function, that means no number can divide, no values of I can divide our num. That means it is a prime number. So at the end of the here, we can return true. So let's see if this function is working or not. Prime number checker, we can have a variable here is prime, as we have to hold the return value is prime checker. Let's put here 7, okay, and print is prime here. So if we run the code now, it is going to give us true that 7 is a prime number. Yeah, okay. What about 71? Let's see. What about 71? It is a prime number. Okay. So we know that our function is giving us our output. So how do we differentiate which problem, which solution should we take? In our case, there are several ways we can go for the time complexity and several other ways which we'll be learning in algorithm course. But one way we can do is while finding the solution for this prime checker but or prime number, we can see if how many divisions or how many iterations this loop has run. We can easily check it, right? And depending on this, we can say if this solution is good or not. We can do this for all the solutions, like find how many times the loop has run. Okay, so here let's do one thing. Let's do let division counter equal to 0. Sorry, division counter equal to 0. I'm extremely sorry. I've just done a JavaScript line here, so no problem. Like I've declared the number of division counter, and inside the if block, if the number is less than equal to 1, we can do division counter plus equal to 1. One iteration has gone, and we can return false and also the division counter itself. We can see how many divisions were done. Okay, and here inside the for loop, we can do is uh, as many times we are going into the for loop, we can do is division counter plus equal to 1, and while returning we will return false and division counter, and here true and division counter. So basically this division counter is going to calculate how many times our loop has run. Okay, so as we are returning two things is we can do is counter here and print this counter while printing is prime. Now if we run our code for 71, we can see is our the whole code runs 69 times. What if we include one more digit here? What if we include 713? Is going to run for 22 times, and it is not a prime number. So let us check if we can get a larger prime number. Suppose 103. Is it a prime number? Let us check. It is a prime number, and we can see that to check if 103 is a prime number or not, we had to run the loop for 101 times, which is not at all efficient. It means the bigger the number we are providing the function, the more the function is running, right? So this can is a solution where you can find the answer, but this is not an optimal solution. Frankly, this is the slowest of all the solutions, right? So we know we have done all this solution in our data structure classes, and we know this works and everything. But as I was saying, today's in our algorithm course, we'll be thinking more about how we can get the best solution for our problems. Okay, so this solution is done for. Let's see another solution to check if a number is prime or not. So guys, let's talk about something. When you are checking if a number is prime or not, suppose the number is 10. At this point, in the first solution, the slow solution, we are basically checking from 2 to 1 less than num. That is, if the user inputs the num as 10, we are checking from 2 to 9. Okay. So, though it gets the solution done, but it is not efficient. We want to make this more efficient. Okay. So, let us do one thing. Let us see one thing that when the input is 10, let's suppose the input is 10, we don't we are checking at the currently we are checking from 2 to 9, but do we really have to do it? Like if you think about it, if we check till 5, like half of the number, if the input is 10 and we check till half of the number, that is 2 to 5, we can easily check if a number is prime or not. The reasoning behind it is, uh, if we are inputting a number, if it is divided by if it is divided and it is not a prime, it has to be divided by at least the half of that number. So we can have 11 here, we can have 17 here, we can have whatever we want, we can have here. So let's suppose we have 100 here. We don't need to check from 2 to 99. We can check for from 2 to 50, because if 100 is divided by, if 100 is divided by any number, 50 must be in it. Half of the number must divide the whole number. That is basically the logic behind our behind this solution. So when we are running our code, when we are running our for loop, we are not basically checking till 2 to n minus 1. We are checking till 2 to half of n. Okay. So if I copy this code, the first code, the slow solution, and in the partially optimized solution here, let's do one thing. Let's make the name slow. Let's make this partially optimized. Okay. So what were you saying? The basics of the basic solution for this problem will be same. We will check if the number is divided by some other numbers, right? But the loop we are using won't be till n up to num minus one. The loop will be till we will divide half of it. So we'll divide it by uh, 2, so it will get half, and we can add, if it's an odd number or something, if we can add 1 here. So now so we can see that for 103, the first solution gives us 101 iterations or loops to tell us that it is true. Okay. For our second solution, let's see how many times it runs. Make sure that we know the range here is basically half of what we have done here in the first solution, like 2 to num. Here it is basically 2 to 4 division 2 plus 1. So it will basically run half of the whole set. So let's run the code. See, we are basically making the solution, the loop time, the number of iterations the loop is running, to half. So this is basically a better solution than what we were doing at the first place. In the first place, we were running the loop for 101 times. In the second case, we are running the loop for only 50 times, and it is also giving us our proper solution. So I would say, depending on the number of loops the function is running, we can easily say this is a better solution than the first one. This is partially optimized, as we will see another solution which is even better than this. Okay. So up to now, we have seen two solutions. One is a slow solution, and another is a partially optimized solution for finding the prime number, to check if if a number is prime or not. So in this regard, we can easily say, with only limiting the loop to half, we have significantly made our function much better, right? The partially optimized is much better than the slow solution. Okay. Now let's talk about the fastest or the best solution for this problem. Okay. Um, according to formula, what we know is, um, when we are trying to check if a number is uh, not prime or not, one thing or one formula we have is, we can check from 2 up to the square root of that number. Up to the square root of that number. Let's see an example here. Suppose the user has inputted 10. Okay, first of all, let's do one thing. We have import math. Let's do one thing. Do one thing. Let's uh, see num equal to 10. Okay, the user has input 10. We have to find if 10 is a prime or not. Basically, we have to check if any number between 1 and 10 can divide it or not. In our first solution, we checked from, sorry, what did we do? We checked from 2 to 9. Okay, this is our first solution. In our second solution, we said we will do half of it. Okay, and this is also giving us our solution. Like for 10, if we run the loop till 5, we'll get the answer if it is prime or not. If it is not prime, it will not be divided. If it is prime, it will not be divided, and if it is not a prime, it will be divided by any number between 2 and half of that number, like 10. Okay, and in our last solution, what we are saying is, We don't have to go till 5 or the half of the number. We can do is we can go to the square root of that number. That is, we can check up to the square root of that number, and it will tell us if it is if it is a prime or not. Let's see what is the square root of 10. Uh, let's do one thing. Let's turn it into int, an integer number, and here let's put 10 and assign it here. Okay, so let's see what is the value of square root of 10. Oh, I'm sorry, we have to print it out. Print now. Okay, so this formula or this logic is saying that if we check from 2 to this number, like the square root of that number, we will find out if the number is divided a prime or not. Okay, let's see a bigger number here. Let's see our first our problem here, 103. In the first problem, we were checking from 2 to 102, right? In the second solution, we were checking, we were doing it only for 50 times. The loop is running only for 50 times as we were going to the half of the number. In this solution, if we go to the square root of that number, let's say 103, if we run this, the whole set of problem will be completed in the checking will be completed in 10. Basically, we will only check if the number is divided by 2 up to 10. You guys get it? So the solution, or if we can do is if we want, we can increment it by 1. If it is odd number, as it is odd number, we can increment by 1. But we can easily see that 11 iterations would be better than the 50 or the 101 iteration. So let us do it. Let us do the problem. Let us copy this. And here, let us do prime check partially optimized. We will change it to optimize. So this is the best solution for this problem. Prime checker. Okay. The user will give us number. We will check if it is less than or equal to 1. And here inside this, what we will do, we will basically find the math square root of the user input, and it's integer. Okay. So now if we run the problem, what will we see? We will see that we are finding if the number is prime or not in only 9 steps. By only checking 9 steps, we can say the number is prime or not, which is very efficient than the previous two solutions. So let's do one thing. Let's Google, which is the largest 4-digit prime number, which is the largest 4-digit prime number. Prime number. Let's do one thing. Like it seems that this is the correct option is A. So that is 999973. 9973. Let's do one thing. Here in your problem, let's run 9973. Here let us run 9973. Here let us run 9973. So if we run the slow solution first, we are basically running the function, running the loop for 9971 times, which is not at all ideal. If the number gets bigger, the number of loops will get bigger, right? And it is too huge. This is not an ideal solution. In our partially optimized solution, what we can see is the loop is running till half. So if the input is 9973, the loop is running for 4985 times, which is significantly better, but not the best. In our optimized solution, what we can say is when we run the code in only 98 steps or in only 98 iterations, we can say is the number prime or not. So easily saying we can easily we can say the last one is the best solution for this problem. So even if we were in our data structure course, if you could do the number one solution, you would get the marks. But in this algorithm course, you basically have to know that among these three solutions, which one should you be doing and which will yield you the best result or best outcome. Okay, this is very important because why are algorithms created, right? It's basically created for specific scenarios and where it will give us the best solution. Suppose there are several searching algorithms, several sorting algorithms. Like, why is the need for having that much algorithms, right? Searching algorithms. There are many searching algorithms. Why do we need that many algorithms? Basically, the reason is depending on your scenario, we will be using different algorithms to get the best result. That is the primary target of our algorithm course, to make the students understand that not just learn the algorithms, but learn where and how to implement the algorithms. Which algorithm will give you the best result, which algorithm will not give you the best result. That is basically what we're trying to achieve in this course. Okay, and the purpose of this today's lab, is only giving you a heads up or giving you a primary description or primary can I say, primary outcome idea of how you can implement this algorithmic thinking in our course or in problem solving in general. Okay, so here I've only done a few the specific solutions here, right? But if we go to the lab file, we can see there are a lot of things here. Okay, so let us do one thing. Let us go one step at a time. There are several installations and imports. We don't need to learn this. This is only for visualizing our problem for this file. Okay. The main thing is that there's also a helper functions, plot side by side. This function is basically called when you are plotting in a graph. Basically, this is a way to plot the outputs we will be finding throughout the solutions. Okay, generate random numbers. This function is for generating random numbers. We don't need to learn this or memorize this. The basic thing, these are basically used here to find the to show us graphically or visually the differences between the different solutions. So here, as we have seen earlier, this is the slow method. In this method, this is prime slow in this function. This has done what we did a bit earlier, 2 to num, which is the worst solution, I would say, the most slowest solution of them all. And here, what we can see is here the slow function is written. Then we can see the partially optimized function, where basically the loop is running for half of the number. This is the partially optimized solution, and the last solution is basically our most optimized. So we're finding the square root of the number. Okay, so the three main functions that we discussed earlier are here, but let us see how we will be seeing it. Okay, so first we can see here is generating random integers. So basically, using the generate random numbers function, we are basically generating an array of random numbers. Okay, and here is the output of the random numbers, 11 through 98. There are 30 numbers in general, and in this graph, we are basically seeing how many numbers are between 0 and 20. We can see there are two numbers. If we see here, between 0 and 20, there are roughly there are two numbers. Between 20 and 40, there are a lot of numbers. Between 20 and 30, there are seven numbers. So we can see is 20, 1, 2, 3, 4, 5, 6, 7. Seven numbers. So basically, this is showing the random numbers between this. How many random numbers are there between these ranges? Okay, this is just showing us there is nothing to memorize here. Okay, so after that, we are basically running our function, running our slow execution or slow function. In an slow execution log, we don't have to understand it. In a way, it will show us how much time is needed, how much divisions or division counter, and how much time it is needed for finding the solution for a specific number in a slow solution. So here you can see is for 11 we are needing 9 divisions, and this is the time that is being needed. Okay, and subsequently we can see is for each number, let's focus on specific number. If we do, let's see here 67. For the slow solution, 67 needs 65 divisions, and this is the time that is being needed to find the solution for 67. Okay, now we will be doing the same thing for the partially optimized function. We can see here, if we focus solely on a specific number for 67, we can see is the number of division has significantly gone down to 32, and the time is also very less. You guys get it? That the time is also very less, and the number of division has also reduced significantly. In the slow solution, we can see is there it required 65 divisions, but in the partially optimized, it only took 32 divisions. Okay, basically the loop ran 32 times. So if we go down a bit in the optimized execution log, or for the optimized solution, we can see is for number 67, it only ran for 7 times. That is, the loop ran only 7 times to find the solution. We can clearly see the time needed for doing this is significantly less than the previous ones. So here, graphically or visually, we can basically see which function is giving us which output, or which is better. We can easily see this. Okay, so here basically this whole solution is based on this. There are also number of divisions, basically showing you how many divisions are needed for each of the solution. Here yellow is the optimized line or optimized output for the optimized function, partially optimized function, the slow function. We can easily see this. For the slow, it took the maximum number of divisions, right? And also the time, it took the maximum number of time. So one thing is, not always we will be talking about the time it took to do a solution, because depending on the device of the individual, the time taken might vary. If the PC is fast, this time can be a little less, and if the PC is slow, this time can go up a bit. So for us, if we check this, yeah, how many divisions we will be needing, that is better. Okay, here at the end of the file, we can also see the complexity classes that there are. There are all the complexity classes: constant, logarithmic, linear, quadratic, cubic. These are all the complexity classes we will be seeing throughout the course, and while doing different algorithms, we'll be talking about this in detail, and also we will be doing this in more detail in the upcoming classes. So this is a very simple slide, if I may speak, and the main purpose of this slide is to show all of you, or give you a basic idea why we will be thinking to find the best solution, or think in an algorithmic way. So thank you everyone. If you guys have any query, you can always email us with your queries, and inshallah we will see you in the next video.